Wow, what a great crowd. Fantastic on a Wednesday morning to see so many of you here. I'm John Holler, the CEO of the museum, and I'm so delighted to welcome you back on behalf of our trustees and our staff and our members, many of whom I'm sure are here this morning, and our amazing volunteers. This is one of those rare days in computer history, and we're so thrilled to have all of you here. Let me just say that if you're here, ordinarily you're hearing me talk a little bit about our Revolutionary series, and that's in a bit of a hiatus now. We're going to resume Revolutionaries in September, but we have a number of programs coming up over the summer that are not revolutionaries but are also very interesting, like this. So I hope you'll check the website for that information. This whole day is made possible by a very special trustee who I'm going to introduce in a moment and who is going to serve as the Master of Ceremonies. And he's also going to do something else that I need to do personally, which is to thank Autodesk for their very generous support of this event today. You're going to hear about Autodesk's role in a lot of what we'll be talking about and looking at this morning, and we're very grateful to have Autodesk do that. A couple of ways that you get involved. So you have these on your chair. It's a card, and you have a golf pencil. And that is a very analog way for you to ask questions, but we do want to hear from you. So as the morning rolls by, please get your questions down on these cards. We'll be coming through to collect those. You'll see our guys as they're coming through, and then you can hand your cards up, and that's how you get involved. Let me remind you, this is a two-part day. We have a morning panel. You're going to hear more about the details of that in a minute. Then we're going to have a lunch break. Lunch is on your own. Please visit the cafe downstairs. We're going to have a few snacks and some water and drinks out here. And then we'll reconvene in the afternoon promptly at 1:30. So please be back for that. You may be tempted to see the Babbage engine get cranked at 1 o'clock. That's okay. You've got a little bit of time to see that happen and then be back here at 1:30. Now let me introduce the man who's responsible for this today and who's going to serve as the Master of Ceremonies. You know, I think we're lucky at the Computer History Museum to have one of the best nonprofit boards in the country. They've built an amazing institution. They provide enormous support. They help in every possible way. And we have a trustee with us today, Michael Hawley, who is one of the biggest helpers of the entire prospect of putting programming together at the museum. Mike had a brilliant career at the MIT Media Lab. He joined our board 3 years ago. He's been responsible for initiating a number of programs here on stage and in this auditorium. He's the architect and ringmaster of a wonderful conference that happens every year at this time, which is the EG conference down in Monterey. We're actually benefiting from the fact that EG is taking place because some of the people you're seeing today are on their way down there with him. Jonathan Knowles, Michael Wright, Brendan Foley have all been EG participants. Mike was instrumental in putting that band back together and getting this day together for you. Please join me in welcoming Mike Hawley.
And the division of the day, I want to just put a tiny bit of color on. In the morning, you've got the artifact and a little bit of history, courtesy of Michael and Nick. And in the afternoon, you have more of the exploration of the modern site. Both are absolutely fantastic. Filled with ideas and filled with interest, and I think you're going to like it a lot. I want to very quickly ask Jonathan Knowles to come up here, and while he's finding his way to the stage, I'll just mention that this strikes me as a real renaissance time for Autodesk. I was blown away. They've acquired Pier 9 in San Francisco, filled it with every kind of magical contraption and gizmo you can think of, biotech research, 3D printing, and lo and behold, it turns out they've developed a fantastic interest in marine exploration of all sorts, using every kind of innovative technology they can bring to bear. So Jonathan, why don't you come up and tell us about your involvement here with this day and with the museum and everything else.
Thank you, Michael.
Thanks.
So this is great to see so many people here today. I'm sure all of you have heard of that product that Autodesk created over 30 years ago called AutoCAD, right? Of course, everyone walks up to us and says, oh, you work for AutoCAD. Well, it's 30 plus years later, and now we make hundreds of products, and as Michael said, we're involved in lots of different things, including recent efforts into Autodesk's maritime research and development. And we're working with Brendan and other people like him to explore, to find out what's next in the world of design and engineering. And that's why it's such a great fit, actually, for us to be here today with Michael and talking about the Antikythera Mechanism. What a fabulous thing it is. You might see us, by the way, out on the bay and other places. Autodesk now has a couple boats. Who would have thought? Big software company like us, but we do, a dive team. We're very active with all that. And how appropriate that we are here when we consider that ancient Greece was the cradle of technological civilization 2,000 years ago. How wonderful that we are here in this valley, the current cradle of technology and civilization. I think we can all agree that. And specifically here at the Computer History Museum, which connects our technology past to our technology future. This is not new to Autodesk, actually. So in 1791, the HMS Pandora, which was the ship that the British had sent to pick up the Bounty prisoners on HMS Bounty, Captain, right, the mutiny on the Bounty, Captain Bligh, all that. And they sent them off. They picked up 17 of the prisoners and then started to bring them back. And they hit something in the Great Barrier Reef and sunk and lost the prisoners and all the crew. And that ship was found in 1977. And an archaeological expedition was sent out there in 1983, about the time that computer-aided design started to get going. And this is a picture from that particular expedition. And they used that it was 1984 by the time they got out there. It was the 1984 version of AutoCAD to actually do the digital work on that site. And these are the actual screenshots from that technology all those years ago. Pretty fabulous stuff. Well, this afternoon, in the afternoon session, after you hear from Brendan, you're going to hear from a wonderfully brilliant woman, Tatiana, who's going to share with you some of the fascinating things going on today with regards to this. We have just finished working with U.S. Navy and the National Park Service to do a reality capture of the USS Arizona in Pearl Harbor. Using LiDAR and sonar and photogrammetry software, we're able to capture things, capture reality, and preserve it digitally. And because it's the models, we can do some real interesting things. For example, right here, this is a Coke bottle that's been sitting at the bottom of Pearl Harbor since 1941. Because it's the data that we've also captured here, we were able to 3D print that Coke bottle. More interesting, though, than that, this next image you're going to see, this is a cooking pot from the galley of the USS Arizona, which we 3D printed and put into the hands of one of the survivors who was on board the ship when the ship sunk. And he just started to weep, of course, because he was now able to connect with something like that. It was great that we were able to do this about a week after we finished the entire project. One of the walls of the Arizona collapsed. And thank goodness that we were able to capture that right before it happened. So, when I think of Michael and when I think of his reconstruction of the Antikythera Mechanism, I can't help but think of this guy, Archimedes, right? The original maker. That's another big thing happening here in this valley right now, is people now have access to amazing sets of tools and technologies that allow them to, sort of do what Archimedes did back then. And I fundamentally believe, and at Autodesk we do too, that the world's a better place when we have more people doing design, more people doing engineering, and when they have access to tools to do it, just imagine all the things that can happen. I hope that some of you will go out after this today and do something, like these folks here. There's a site called Instructables that walks you through how to make things, and there's a little company called OpenROV that lets you, for about $800, get the bits to make your own underwater ROV and actually start doing archaeology, doing science, doing engineering in the water yourself. There's no excuse for you to not be doing this, or maybe for some of your family members to get them involved in doing this. So, with that, why don't we turn things back over to Michael Hawley, and let's go back to ancient Greece for a little while. Sound good?
Okay, is that a clicker?
There we go.
Great. Can I have my picture, please? I think they're switching the computer feed. What I thought I would do is take 6 or 7 minutes and just give us all a framework so we're on the same page. And I will tell you in advance, I'm going to get a lot of bits of this story wrong and distorted and warped, but the folks who are here can spend the rest of the day straightening it out for you. There's Antikythera. It's that little flyspeck island, or as I've learned this morning, Antikythera from the Greeks. It's south of Kythera. Kythera is there a laser pointer on this? There is somewhere. Kythera is here, Antikythera is there. It's a small volcanic island in the Aegean with steep coastal shelves, a miserable place to be, just a few sheep and annoying people. And the story goes something like this. In 1900, a Greek vessel filled with sponge divers anchored off Antikythera. A fellow went down and he came up, he was delirious. He'd seen arms and legs and body parts. And the captain figured, well, this knucklehead has been out in the sun too long, he's drank too much ouzo, send somebody sober down. And so they did, and by sending people down, this is what they were wearing at the time. And this is what they found. It wasn't body parts, it was bits and pieces of statues. And it proved to be the most spectacular shipwreck ever found in the Aegean. Brendan calls it the Titanic of the ancient world. All of these miraculous things came up. Turns out the shipwreck was dated to about 65 BC, give or take, so it was more than 2,000 years old when found in 1900. And the archaeological authorities funneled all these artifacts back to the National Museum in Athens, where I took these pictures. And some of these things are just breathtakingly beautiful. I mean, marbles, bronzes, monumental pieces. I'm sure somebody will have more to say about that later. The site was visited, just sort of tickled really, by Jacques Cousteau around, I don't know, 1960, give or take. But they didn't find very much and they didn't do very much. There's a tremendous amount still waiting to be known. In 1902, back to 1902, the curators were still tearing open wooden crates at the museum in Athens. And one fellow ripped open a box and he pulled out the famous rusty hunk of metal that blew his mind. And it looked like that. And it blew his mind because it's a machine. And it's not just a machine, it's got gears and axles and things. It almost looks like clockwork, even though you can't see very much since it's 2,000-year-old rusted bronze, I guess. I think it's bronze. But there's teeth. And the thing about that is that, you know, clockwork didn't appear in Western Europe until 1000 AD, 1200 AD. So this was an artifact out of time. And it turns out it's so precise in its workings, just fantastically sophisticated when you really understand what it does. This is a little like going underneath a pyramid in Egypt and finding a black and white TV. You wonder, how the fuck did that get there? You know, and what were they watching? And inside, as you will learn, there's all sorts of gears and clockwork, and it's unbelievable how it works. And the man who figured out more of that than anybody else is with us, Michael Wright. This is a picture I snapped of Michael in his backyard. That funny little contraption, the brass thing, is a very sophisticated sort of sundial. All I know is that it matched the time, atomic clock synchronized time on my iPhone to within about 5 seconds. So suffice it to say, Michael really understands how to make precision things out of brass. And there are, I think, very few people on Earth who had the right mix of skills, as you'll see, to be attracted by figuring out that device and demonstrating the sophistication of it by building a reconstruction of it. So I'll mention just one or two other things about this in the spirit of hopefully getting them wrong, and Michael can sort them out, and then we'll bring Michael up to do that. You twiddle a knob, it sets a needle to a given day in a, let's say it's a perpetual calendar year, and this little white ball in the socket represents the moon. It twiddles around, it's half white, half black, tells you the phase of the moon on that day of the year, the position of the moon in the sky. The other needles give you the positions of the 5 planets known at the time. It's a geosynchronous, a geocentric model, not Copernican. That's understandable, we'll give them a little slack for that. But it's pin accurate to a quarter day per year. It takes into account leap year and some other magic things. On the flip side, there's another dial that gives you approximations of when the next solar or lunar eclipse could occur. And then the final dial, this one here, I think of as sort of like the cuckoo in a Bavarian cuckoo clock. That one tells you the city and the date of the next propitious Olympic Games, because once the planets are in alignment and there's no eclipses to blot out your marathon, you're good to go. So that's a very bad account of what this thing actually did, and I would love it, Michael, if you would come up and sort it all out for everybody. Michael Wright.
What I discovered for myself, nothing to do with school, nothing to do with my parents who thought I was some sort of small monster, I found I was a mechanic. What I mean is, I think with my hands as well as I hope thinking with my head. And I think this is going to be important for our story because it may. I think I'm the only person who's got up close and personal with the original bits of the Antikythera Mechanism, who has that sort of practical experience. And I think having that sort of experience, you see different things, you understand different things, and I went on to, as part of my research work, to make first one and then another model. This is over on your left, is my first model in its present incarnation. You'll hear more about that presently. And it's full size of the original. And in the parts that exist of the original, it's a fairly close copy. Obviously, there's a lot that one has to, well, the blunt word is guess. But guess intelligently, I hope. So here we go. I went to work as a curator at the Science Museum in London, and that's an example, one of the more polite examples of the sort of thing I was looking after, heavy engineering. There's a steam engine, it's the sort of thing I looked after. But it was, while I was there, I got involved with this thing, which you may recognize, in its early stages. Some of you will know the name of Alan Bromley, an academic from Australia who set this whole reconstruction of Babbage's engine going. Alan had become a Babbage scholar, and he came over to study in England the remaining Babbage artifacts and Babbage's notebooks and drawings and so on. And when he'd finished looking at the drawings in the library, he said to one of my colleagues over there, okay, I understand what it's meant to do, but I can't understand how it could have been made. So my colleague in the library said, go and see a chap called Michael Wright. So Alan and I got to know one another, and from talking about how you'd make a Babbage engine, we got on to trading all sorts of mechanical curiosities. And there came a day when I told him about my interest in the Antikythera Mechanism. And what did the rotter do? He stole the project from me. Because he had time for research. I had none. He had a certain amount of project money. I had none. He had carte blanche with his department to study whatever he found interesting. I had a specific instruction from my line manager that I would have nothing to do with that ancient Greek thing. He couldn't say Antikythera. Even, he said, in my spare time. So this gentleman was a bit of a rogue in private, we all knew. So I used to say, I said to him, all right, Dr. B, I won't tell you his name, no name, no pack drill. How far does your line manager try to control what you do with your spare time? He was trying to get me to sign a legal undertaking. So he just went beetroot red, and I left the room without signing his undertaking. And that's why I was never promoted. Anyway, here, this thing. There's a picture on the left of Alan Bromley with the beard. Reg Crick, the man whose tie is hanging forward, the draftsman who did a lot of the drawing for the parts of the reconstructed engine. That, believe it or not, is me leaning over the table at the back in the days when I had more of a head of hair. But you can recognize the chain for the pocket watch. Alan is going to come into my story again in a moment. A brief digression. I wonder how many people recognize this part of the difference engine, and I wonder whether, for your example, this component, any of them, has given you a bit of trouble. If so, I have a story to tell about that in private. It'd probably better be in private. Going back a few years, fairly early on in my time in the Science Museum, this paper came out, late 1974. Gears from the Greeks was the first thing I ever heard, or read about the Antikythera Mechanism. It was absolutely stunning. Gosh, I thought I'd like to be involved with something like this. But this Professor Price seems to have done it all, sewn it up. The only problem was I couldn't understand a lot of what he'd written, a lot of his argument. I thought, well, this must be my fault, I must be stupid. Actually, I was stupid because, well, I'm embarrassed to tell you how this turned out. I had to leave this aside because my steam engine's called, and things. And but I came back to it about 10 years later. That's just a picture of the museum's store in Athens. It wasn't a matter of tearing open a box, it was a matter of kicking over bits and pieces on the floor, I think, to find the parts of the mechanism. Shall we say turning them over. We've seen that already, so we'll go through it. I want to talk about this. We're talking about where the mechanism came from. All I'll add to what Mike said, if I can do this, is on my map, here is Antikythera, there's Crete, there's the Peloponnese. This corner of the Peloponnese is Cape Malea. Ancient sailors had a saying, which has come down to us, if I can do it, Maleas de campsas epilathouton oikidi. If you go around Cape Malea, you can forget about getting home. It's a dangerous part of the world. So it's not surprising that there was a shipwreck there. After all, what you've got here is a rock in the middle of a busy shipping lane. And the wreck looks as though the ship positively drove against the cliff and went down onto a ledge straight below the cliffs. You'll hear more about the wreck itself from Brendan in a moment, so I'll go light on that. The ship was almost certainly heading west from this part of the world. Coins from the ship give us a pretty clear dating to 70 to 60 BC and indicate a recent port of call on this coast of what's now Turkey. Most of the artifacts found in the ship come from this region. Most of them were probably contemporary with the wreck. A few, like this rather special fellow, were thought to be several hundred years old by the time they were shipped. So it's a mixture of luxury goods. And the puzzling thing that I'm here to talk about is part of that luxury cargo. Don't let anyone persuade you that because it was on a ship it had to be a navigational instrument. There is no way of using this thing for navigation. Let's hit that one on the head. That's more like what it looked like in 1902. The bit that Mike Hawley showed you is this piece here. You can just about recognize the profile. You can see a lot less of the detail, but you can see some bits that were missing by the time Mike Hawley's photograph was taken, particularly some woodwork, which is part of why the box for mine is the strange shape it is. I've taken account of that. Okay, well, 10 years after this is Price's reconstruction of the thing. What we have is a wooden box with a bronze gadget inside it. I mean, the wooden box frames it. A bronze dial front and back. On the front dial, 2 rings. The inner one is the zodiac, divided into 360 degrees. So celestial longitude, for those of you who know your astronomy. The outer ring is a 365 day annual calendar, and I'll come back to that. On the back, two more essentially calendrical dials. The whole thing worked by turning a spindle at the side through gearing contained inside it. Okay, that's a summary of Price's reconstruction, and so far that's okay. I believe all of that, but none of his details right. Almost none. And we'll probably come to that. I had to go back to reread Price, as I say, about 10 years after that paper came out, when I got involved dealing with, I didn't mean to do that, wrong gadget. Dealing with this thing which came into my museum, which we believe is the second oldest set of gear wheels in the world so far. And I designed and made the reconstruction. It wasn't my business to make reconstructions at the museum, but the workshop was on a go slow and we were having an exhibition. So workshop manager said, well, first of all, we'll have to wait till the right draftsman's free to draw the parts. Oh, that'll be 6 months. Oh, and then we have to find the right workman in the workshop to make this thing. It's not everyone can do it. So I ended up saying, well, get lost. I'm taking a week's holiday. And I came back with it made at home. This is Professor Derek de Soller Price with a reconstruction that was made for him, which is all wrong. But he had every right to be proud of it because, it was a stage. I met Price when I was working on that other gadget. He actually came to see it and me and my colleague who was working on it with me. My colleague was talkative, and I hardly got a word in edgeways with Price, and a fortnight later he died. I don't think there's a causal relationship, but it means I could never ask him any questions. But by then, I had realized why I hadn't understood his paper. A lot of it is rubbish. You may think I'm insulting the US of A because he was a professor at Yale, but he was English, so I'm allowed to do it. So anyway, what happened was, I said Alan Bromley took over my project, and I had to run with him or be left behind completely. So we both went to Athens. We got permission to study the thing. This is, again, believe it or not, me, about 1991. And that is that big fragment of the mechanism, the face you recognize downwards. I'm looking at the back of it. And we... Alan took a lot of photographs. I went all over it with not just this magnifier, but all sorts of magnifiers, and got very down and dirty with it, and measured it using a homemade measuring jig. Then devised homemade apparatus to allow me to do linear tomography with it, which was necessary to separate out what happens in the different layers. I told you this is all embarrassingly low tech. Linear tomography was devised in the 1920s for locating shrapnel in the human body. It worked very well for separating out the layers of cogs in this thing, up to about 8 layers thick. That's a photograph of the thing, is published in a book in 1903, and therefore that was photographed in 1902. That's photographed by Alan Bromley and me in about 1991. You see how bits have gone missing. Let's go, if we could just go back, watch the transition again. And that's one of my radiographs showing that's a straightforward plain radiograph showing different layers inside, which is the sort of stuff I've worked from. You've heard, I'm sure, about high-tech, the jargon is cutting-edge computer-aided tomography that's been done on it. I've had nothing to do with that. I've been excluded from it, actually, and I have no access to its results. So all that I've done has been done with more, well, the old-fashioned way, as they used to say in the Navy. So in 2002, I was ready to model the front of the instrument, and 2004, I was starting to think about the back. A conjectural completion about 2005, which is beginning to look recognizable. Small modifications in 2006 and 2008, when the other guys in the story published, and I was able to modify things a little bit. But the general perception is that it's what the other guys have done, the Antikythera Mechanism research group, that have told us all we know now. Well, all I'd say is, if you look hard, you'll realize that actually their work is built much more solidly on mine as a foundation than they're admitting. I'll give you some perspective. My model took me about 1,000 hours to make, working at nights and weekends. I suppose some of that was thinking time. But it's made largely by hand tools. Most of it is made with a set of tools I could put in the pockets of this coat, plus a bench vise. When the group published their results, it took me an afternoon to modify what I'd done to fit with those parts of their results which I'm sure are right. So the alteration between my provisional reconstruction and what we have now is quite slight. What the group have done magnificently is, and the author of the system is here, I won't embarrass him by naming him, unless he asks me to, is they've done a magnificent job of getting images of the surfaces which allow them to read the very fine lettering on the surfaces of the original fragments, which is very, very hard to read. I got an epigraphist on the job, and he started and he gave up. So that was the end of my effort on that. Then I built a new model about 2009. We'll come back to later. I would bring that one to show you, except that it's on display in Athens at the moment. That's the story of my model making. And now I'm going to, it's an astronomical gadget, so I'm just going to remind you the very basic astronomy that you need to understand it. And we start with this rather fanciful picture of the night sky. Here is our ancient astronomer looking west. That's the new moon, so he's obviously looking west. And it's in Taurus, the constellation Taurus, which means it's spring. It means the sun is in the next constellation down, Aries, which is around the vernal equinox, the spring equinox. So there's Taurus, there's Gemini above it. And the stars form, as you know, a fixed pattern, which rolls over us night after night, but is shifted a little every night, so that night by night, the stars we'd see at any measuring point, say the horizon, at sunset, are slightly different. So a few days later, if you look at that one now, watch, Taurus is a bit lower in the sky at sunset. The moon, incidentally, has moved along up, but never mind. And it shifts night by night until, if you watch, after 365 nights, or thereabouts, the pattern of stars is exactly as it was when you started. So that's the year. The year is to do with that shift in the way we see the stars against any fixed register. Let's go back to that first picture, and now we'll consider the moon. Here is a thin crescent new moon. It's a day or so old, let's suppose. And a few nights later, it's moving up to the left at sunset, until finally he looks the other way. He looks east just before sunrise, and there is the new moon, now by the Pleiades in Taurus. And it's about 27 days later. If I go back to the last one, the one before it, here was the moon early in the month. At the end of the month, it's back in the same place in the sky, but you see it, of course, the old moon you see in the morning, just before sunrise. So that's one form of month. But there's another form, that's strictly the sidereal month, or what comes to nearly the same thing, the tropical month. And maybe we'll disentangle those at question time if you want. Go a couple more days, and there is the next new moon, now by the foot of one of the twins in Gemini. And that's 29 and a half days, roughly, 29 or 30 days. So that's a different sort of month, and that's the sort of month I'll be talking about mostly in what's to come. Properly speaking, it's the synodic month. In other words, the month measured by the sun's position relative to the sun. Okay, so we've got years, we've got months, both defined by the sky. And the numbers are awkward. There are the numbers, approximately. Consider the top and bottom ones. 365 and a quarter days, 29 and a half days. Months don't fit into years exactly. It's annoying. Particularly as, for calendrical purposes, all the Greek city-states that we know about their calendar used a lunisolar calendar. In other words, they worked both by the year for some things. I mean, the seasons go by the year, the time when it's suitable to sail, the times when it's suitable to reap your harvest. They go by the year. administration, civil matters tended to go by the month. If you had a debt, the interest was payable at the new moon. We get that from Aristophanes. But there's no subtlety in this astronomy at all. You see, it's just a matter of observing what happens in the sky and keeping a note and counting. Now, this is a thing that particularly the Babylonians were really good at in Mesopotamia. And they kept their records on tablets of clay, like this one. This one happens to tell the story of the flood, but never mind. It's an illustration of the sort of thing, and it shows the sort of size of these clay tablets. They're handy size. They kept astronomical records from a very early date, and fairly thorough ones, and they were really interested in counting. Babylonian astronomy is, it's that one again. Babylonian astronomy is really, they had no concept of kinematic motion, of what was going on in the sky, but they were interested in numbers, timing of events. So we get this thing which we know by a Greek name, the Metonic period relation, but it existed in Babylonia beforehand. If you multiply up, you find not those approximate figures, but if you actually count, 19 years contain very, very closely 235 months. It's synodic months. That's a very useful period relation, as we call it, years to months. And the other one is really, it follows directly from it. That 19 years, there are 254 tropical months, to the same approximation. It's good to say, well, it won't get, the position of the moon, according to this thing, won't go wrong by as much as 1 degree in over 500 years. It's good. So, now we're ready to go to the instrument. Okay, that was the astronomical interlude. The first one. Here's the back of the instrument, and I'm starting with the back because we know more about it, really, than we do about the front. It's less badly wrecked. The top, as I say, there are 2 calendrical dials. The top dial is absolutely a straightforward calendar. Straight away, each of these divisions is a month. A synodic month. They're all named. They go round in 5 turns on the spiral from there to there. There are 235 of them, 19 years. The beginnings of the years are marked. Now, because there are about 29 and a half days in a month, in your calendar, each month has to have either 29 or 30 days. Because if you multiply that up by 12, you don't get as much as a month, as a year. You get about 354 days. Some years have to have a 13th month. This array gives you a plan for which month is a full one, which one is what they call a hollow one, with only 29 days, and it tells you here which day of the month is to be left out to keep things as even as possible. It also tells you which years should have that 13th month. So this is, as I say, a straightforward calendar scheme. The little dial here, this is the one which people have remarked on because it has the different Greek Panhellenic games. I don't know whether it's clear enough to read, perhaps I don't know whether it's my photography, or I think it's more my photography than my engraving that's at fault, that you can't really read that says Olympia. But the different Greek games happened either on a 2-year or on a 4-year cycle. So on a dial with a pointer going around once in 4 years, you can put them all in. People have remarked on this as being an odd one out. It's, shall we say, social, not astronomical, but I disagree. I'll come to a very good astronomical reason why you should have such a 4-year counter here. And anyway, it's a useful reality check, because everybody knew which games there would be in any particular year. So it's a very quick way of checking you've set the thing to the correct year. The other little dial on the other side is conjectural. Amongst the inscriptions, we have a note concerning the 76-year cycle. but on the bits that survive, we don't have any indication of it. Well, this part of the dial and any gearing that might have been behind it is missing. So conjecturally, the 76-year cycle, 4 times the 19-year cycle, has to be there somewhere, and this is the best place to put it. So that's where I've put it. It has two significances. One is, if you remember the numbers, everyone knew a year was 365 and a quarter days, roughly. If in 19 years, therefore, you've got an untidy number of days, something plus 3/4, by multiplying the whole lot by 4, you had a period relation with 76 years, however many months it is, 4 times 235, who's quicker than I am, and a whole number of days. Very satisfying. The other purpose of this period relation, we call this the calypic cycle, is that calypic cycles got used for things like astronomical chronology in much the way we would use a century. It's a 76-year interval, so you can talk about the first, second, third calypic cycle from when they started in 330 BC. So that's that dial, wholly calendrical. Let's back to the full back and zoom in. We're going to zoom in on the lower back dial, and this depends on another period relation, which was found out in Babylonia and then came to the Mediterranean. Don't be frightened of the name. Actually, that's a modern name, well, given it by the 18th century astronomer Edmund Halley. Never mind. He made a mistake. It's a Babylonian word, but it doesn't mean what he thought it meant. The significance is this. If you observe an eclipse and you note exactly the style of the eclipse, how full was it, which way was occultation, and so on, you can be pretty sure that 223 months later, there will be just the same style of eclipse, only it'll be about 1/3 of a day later. You see there's this 1/3 of a day built into this cycle. So after 223 months and 1/3 of a day, the pattern repeats. I won't go into what these other quantities are, but these are what make the eclipse cycle work. We can talk about them at question time if you're interested, but I'm not aware you really came for an astronomy lesson. I'll just mention that you will come across this anomalistic thing later. You have to. You've got to have it. So we go to the lower back dial, and here is a scale of 223 months set out in 4 turns, but the only entries on that are where we can expect an eclipse in the pattern. And it tells you whether it's an eclipse of the moon or sun in that month, or both, and it tells you what time of day to expect it. Now, as I told you, it'll be 1/3 of a day later each cycle. So we've got a subsidiary dial which adds a correction. That's the Greek letter eta, standing for 8. These two symbols mean 16. So it's telling you how many hours to add to the time given in the main entry to get the eclipse time right in the particular cycle we're in. This pointer moves from one sector to the next in a full cycle. And there are 3 sectors. So what this does is it doesn't, be clear about this, it doesn't tell you you will see an eclipse. It tells you the possibility of there being an eclipse. Of course, many eclipses due of the moon, which happens exactly at full moon, may happen during your daytime. Many eclipses of the sun may happen during your nighttime. And we all know that eclipses of the sun are only visible over a small geographical region anyway. So, or the nature of the eclipse you see varies with where you are. So you don't see the whole of the pattern any time, but this gives you the possibilities to look out for. By analysis of the data here, and the left side of the dial again is reconstruction. This side, we have only a chunk of it from about there to about, we have about 1/3 of the right side of the dial altogether in 2 pieces. and a tiny third bit. By analysis of that data, it can be shown that this sequence, which isn't perfect, it shifts slowly in time because the Saros cycle isn't perfect. It's only approximate. And so you can match this sequence best to a sequence of what we believe were actual eclipses that started in 205 BC. Now, I don't think we should then conclude that the instrument was made that early. I think it much more likely that what was going on was that the maker of the instrument, or the designer of the instrument, took a pre-existing record of an eclipse sequence, and it was old data when it was built into the dial, established data, and perhaps the designer didn't realize how the pattern shifted with time and would start to go wrong in due course. Anyway, how long was he planning this instrument to go on working for? Most gadgets are designed with a recognition that their lives will be limited. This one survived longer than most. Okay, so that's the back dial. Now, we're going to talk about the front. But first, I'm showing you what you see with the back removed. Firstly, you can see I made this model out of scrap metal. That's an office nameplate used as the frame plate. I didn't lever it off the wall. But what I want to make several points about the displays I've just been discussing. The first point I want to make is there's a serious design blunder. Okay, let's go back. When there's a sort of slidey thing, whether it's the hole pointer or not is another matter, which is engaged with a traveller that travels in the slot, so that as time goes on, the slider tells you which turn of the scale to look at. In each case here, my slider is indicating that you look at the, here this part of the scale, here this one. Sorry, I can't hold it steady enough. The next to last one. Now, if you wind on carelessly and come to the end of the slot where it stops being a sort of spiral, and it's not a true spiral, it's a set of semicircles, by the way. And if you go on winding, you'll have a smash. I did it within about 5 minutes of setting up this display. It's easily done because you tend to be looking at the front as you turn the knob, and then suddenly you've caused trouble. So that's a serious design blunder in my view. Second thing I was going to say about it is the astronomy is not subtle. I've tried to show you it's absolutely almost bonehead simple. It's a matter of watching the sky, counting, recording events. The third thing is the gearing that drives those pointers is, once you've got gearing at all, which seems to be a Hellenistic invention, from somewhere around 300 BC as far as we can judge. Once you've got gearing, this is absolutely straightforward too. The gearing to drive those pointers. There's nothing subtle about the astronomy. There's nothing, which is essentially Babylonian. There's nothing subtle about the mechanization of it. I'm not trying to drag the instrument down, but I am trying to provide an antidote to some of the hype that you'll see in print, which suggests this was an amazingly sophisticated device, perfect in its conception and execution, and just unbelievable. Nonsense. You'd better believe it because it's there. And if you find it incredible, then you need to adjust your set. So far, it's actually quite unsubtle. Just wonderful that we have evidence that this sort of thing was done at the time. Now we'll go to talk about the front, and I'm going to talk about a bit you can see here, which, although it's embedded in the back, has to do with the front. We at least have enough of the front dial to know what it looked like. Here's a photograph of it, again from my model, because it's easier to understand. The inner ring for the zodiac, divided into degrees. The outer ring for an annual calendar. Now this is, so you can think of it as a sort of flat projection think about the inner ring as a flat projection of a celestial sphere. The outer ring is for a calendar that we call the Egyptian calendar of exactly 365 days in every year. This was a very good calendar for astronomical purposes because it's utterly predictable. There's no fiddling about, is this a leap year or not, because they didn't have leap years. The leap year was, as far as we know, first formally introduced in Julius Caesar's calendar reform sometime after the Antikythera ship sank. But what they knew perfectly well was that the year was about 365 and a quarter days long. What they accepted was that every 4 years, the astronomy would slip a day against the calendar, or vice versa. In other words, the equinoxes and the solstices would happen a day later in their calendar. And to allow for that, the calendar ring is movable. I'm sorry, that's the wrong button. There we are. So there's the calendar ring taken out of its groove, and you see a series of little holes, 365 of them, and a pinhole in the ring, and there's the pin that actually marks New Year's Day in the calendar, and every 4 years you'd take the pin out, shift the ring round one day, and put the pin back. And that's why you need a counter of the 4 years, which we tend to think of as showing the Olympic Games or whatever. Nonsense, it's for doing this. That's the front dial. Now, what happened? I'm showing you. This has got out of sequence, I think, but anyway, I'll pass over that and come back to it if I need. I'm just showing you why I tend to illustrate things with pictures of my model, because the original really isn't very easy to understand. That's the view I was studying on the table in the earlier slide, and very puzzling it is. But we're going to be talking about a bit that's just here. These wheels are sort of broken in half, like somebody sharing a set of biscuits. The stuff is absolutely terrifying to handle. When I first went there, the fashion in those days was to wear cotton gloves. So I got my gloves out, and the curator said, "Mr. Wright, thank you for thinking of bringing gloves, but take them off again, please. Less of it will come off on your bare skin." It's like handling very heavy, dark green, flaky pastry. We're going to be talking about this bit here in a moment, but first, okay, let's do it this way. I think I'd forgotten I'd remodeled the talk before I sent these slides off to DAG. We know, Price got us this far, that on the front dial we have pointers going around indicating the position of the sun and the position of the moon and the date. Either 2 or 3 pointers. Come back to that. Now, the moon is very obviously tricky in its motion. It doesn't take much subtlety to spot that it moves at an unequal rate across the sky night by night. It moves sometimes faster, sometimes slower, with a pulse. That pulse is not quite an ordinary month long. The length of the pulse is actually what we call the anomalistic month. Ancient thinkers tended to regard the most natural and proper motion as being uniform motion in a circle. And when they saw a thing like the moon moving sometimes faster, sometimes slower, they said, an anomaly. This is what we call the lunar anomaly. Or, now that we have several, the first lunar anomaly. But for them, just the one. And so the moon sometimes goes faster, then slower. The point at which it is at its fastest and at its slowest moves slowly round the sky, because I've said that period is not quite a month. So to model the motion of the moon accurately, we need to imitate the pulse and the fact that it shifts round the dial slowly. This is how we do it. The anomalistic, this you'll recognize as the gearing you saw earlier in the back of the instrument. here is the center of the hand on the eclipse prediction dial. That's the center of the hand on the calendar dial. So you're looking at it with the top is to the right. And on the way, the gearing feeds through from here. So on the way to driving the pointer that represents the Saros cycle, we have this big wheel. We have to, because the Saros cycle is 223 months. That's a prime number, which means if you're going to make it into gearing, you've got to have a wheel at least as big as 223 teeth. 223 or 669 or whatever. 223 it is. Now, what the designer has done is to build his little pulsing gadget onto this, and you'll see why he's built it on in a moment. Here's that wheel seen in perspective. The motion on this point square that I'm pointing out now is at the end of the train driving the month pointer. By the way, that's a design disaster. Perhaps I'll come back to that. So this, as you drive the thing forward, this revolves at the right speed for an average month. But it doesn't go to the month pointer. It comes here, and it has a wheel on it. And that drives a wheel with the same number of teeth. But what I want you to notice here is, if I go back one, is that this stud on the wheel is stepped. So this wheel and the one that's going to go on top of it, like that, turn about different centers. The bottom one has a pin in it, the top one has a slot in it that embraces the pin, and so this wheel goes round at a steady speed, one average month. So does the bottom wheel here. The wheel on top goes round again once a month, but now it has a pulse to its motion. At the point in its motion where the pin is at the inside of the slot, it's going faster. When it comes halfway round and the slot towards the center and the pin is at the outside of the slot, it's going slower. So then we take that pulsed motion back to the center to a separate coaxial spindle in the center here, and it's taken down and through to the front dial. So there's the pulse built into the motion. Now, what about the fact the pulse has got to shift round the dial? Well, that's why it's all built onto the... that brace just holds it all together. Now you recognize the assembly. This wheel it's devised so that wheel goes round in the box at the right speed for the anomaly shifting round the front dial. That is quite subtle work. And this is an interesting piece of design, and so far, quite a good one. So let's look at the front dial with just the sun and moon pointers. And it rather looks like I've put tissue paper in there, but it's done through some rather primitive photo retouching system, which is all I could do. Low tech, as I said. So here's the moon pointer. That's the place of the moon in the sky. Here's the sun pointer. This little black and white bead shows the phase of the moon. It's simply working on the relative motion between the two. It's utterly independent of everything else inside the box. It purely works on a pair of gears hidden under this dome, which you can think of as representing the Earth at the center of the Greek universe, the Greek cosmos. Oh, one other thing here. We have to show the date, so this could be an extension to the sun pointer, except I believe that the sun also has a pulsing motion. It's less exaggerated than that of the moon, it's slower, it's better organized, it doesn't shift around the dial, not as far as ancient astronomy was concerned anyway. But if we build that pulsing motion in as I have, we have to have a separate pointer without the pulse for showing the day of the year. There is another way, another scheme for doing that, which you may have seen in print. There are people who believe that this dial was unequally divided to allow for that solar anomaly. Well, I don't believe it was. They haven't got enough of the dial to be quite sure that their evidence shows what they say it shows. The jury's still out, frankly. We'll go on. At this stage, I used to feel I was on very shaky ground. I used to have to start to explain myself, to argue for why I've reconstructed a set of pointers for the planets. I don't have to do that anymore, because the ongoing job of reading the inscriptions on the instrument shows that I was right. It did show the positions of Mercury, Venus, Mars, Jupiter, and Saturn, the naked eye planets, the ones they knew about. So we have 5 pointers for the planets, what we think of as the planets. They included Moon and Sun as planets, so we've got 7, and an 8th pointer for the day of the year. The mechanism for driving these planet pointers is almost wholly lost. It would have been straight behind this dial and in front of the fragment that we have behind it. You'll see the relationship of the two if you come to my demonstration in the lunch break, when I'll strip the dial out of the thing and you can see the space inside. But it may be that the mechanism for the pointers dropped out complete. It's not my telephone. And if it did, possibly it's waiting to be found. I fear it's likely it's fallen into a lot of very small pieces and we'll be much more lucky. Anyway, for now, we have to just use our imagination to reconstruct what's missing. And there are 2 ways of doing it, so far suggested. First of all, you have to understand the problem. In an orrery, which many of you will be familiar with, a model of the heliocentric universe, the Copernican universe, with the sun at the center, it's a pretty good approximation to have the planets going around in circular orbits at uniform speed. But in a geocentric planetarium like this, it won't do at all. Because the main thing we know about the planets, after all, the name planet means a vagabond, a wanderer. The main thing we notice is they have a very strange motion in the sky. Here's an illustration of, now I'm embarrassed to say I've forgotten what book I took this from, but this is charting the retrograde motion of a planet at some date in the 1950s. Now the planets, like the Sun and Moon, we think of them rising in the east and going to setting in the west, but they're always crawling the opposite way. They're crawling from west to east against the pattern of stars. So are the planets. But although they go on average from west to east, see, this was May the 13th, there comes a point where the planet stops dead and goes back the other way against the pattern of stars. This is in Capricorn, and then stops dead again and goes off forward. This is what we call the retrograde episode, and anyone who follows the rubbish in the newspapers called a horoscope will be familiar with the term retrograde episode, and possibly with these moments, the stationary points, or first and second stations. So a geocentric model of the universe that doesn't do something like this simply doesn't, you're just not in business. So nobody's going to want it. It doesn't show what you see in the sky at all. So we have to find a way of explaining this bizarre motion of the planets. Now, remember that the orthodoxy was that motions should be uniform circular motions. The first news we have of a tolerably satisfactory solution seems to date from around 200 BC. It's reported much later, but that's when the man who was involved with it, Apollonius, was alive. And he's combining 2 circular motions to get the effect we want. E is the Earth. M is a point that is traveling around the Earth with a steady motion, which is the average motion of the planet. P is the planet itself traveling on another circle around M. So if I can do this, this makes loops like this as it goes round the sky. And if we get the speeds right, at the moments when P is on the inside, it can be going that way faster than the point M is going that way. In other words, we get the appearance of the planet going backwards, which is what we want. And I believe this is what was built onto the front of the instrument on top of what we see here. This big wheel goes round once a year. And I'm showing how I've built in this model. What I've done in the second model is slightly different and actually rather better, but the same in principle. I mean, when I say better, I mean it's mechanically better and it follows the traces of the original more closely. I built this in the first instance really as a demonstration of what was possible, rather than an attempt to reconstruct exactly what was there. You'll have to remember, back in 2001, 2002, when I was designing and building this, the atmosphere was that it's just incredible to think that the mechanic of that time could have built such a planetary model. And I was trying to show that it wasn't so. So here you have that wheel that goes round once a year, and that's an epicycle, as we call it, the circle moving on top of the around for Venus. Here's a little one for the Sun. I'll come back to that in question time if you want. That does the slightly unequal motion of the Sun. On there, I'm going to place an epicycle for Mercury. Mercury and Venus, the inferior planets, the ones on the inside track between Earth and the Sun, they go round on average at the same speed of the Sun, but turn about the epicycle turns about its own axis at its own peculiar rate. So that's easy. And there's the gearing to do it. And there are the levers that pick up the motion and transmit it up to hands on top. Sun, Mercury, Venus. The superior planets, the ones on the outside track, outside Earth, Mars, Jupiter, and Saturn, have to be treated differently because the model is the other way out. Here, the epicycles travel at the rate of the Sun, but they go round the Earth at their own peculiar rates. So each has to have its own big platform to go round on. So 3 different units. But they all work much the same way. And for example, here is the one for Jupiter. This is wholly conjectural, but it works. Frame plate, well, what it comes to in the end is that there is the epicycle which drops in there and is driven through a chain of gears. And it works well. We put it together. That's the underside. That's it put together. That's it even more put together with the stationary wheel in the middle that it crawls round. There it is in the box with its lever on. If you built it all up without the box, you get a monster that looks like this, like a sort of multi-tiered mechanical wedding cake. That seems to me to exaggerate the height of it and the complication. It's all inside that box there, and you can see later. More recently, I did this back in 2001, 2002. 10 years later, somebody came up with another way of doing the planets, which involves fewer moving parts, building on there. 2 sets of people came up with the idea simultaneously, and to be fair-minded, I've taken illustrations from both of their papers, without permission, but never mind. You won't tell on me. Now, this is quite an ingenious way of getting nearly the same effect. It's a development of that thing I showed you for the lunar anomaly with the pin and slot mechanism. Here we have a big thing that rotates at the rate of the Sun. What the pin and slot mechanism does is it subtracts a motion for these wheels which go through and carry the pointers. So the motion of the once-a-year motion of the Sun is subtracted by these wheels at a varying rate. And the point where the pin is at the middle of the slot and that motion is fastest, the subtraction is so great that it makes the driven wheel in the middle go backwards. So it achieves a retrograde effect. The difference between theirs and mine is this, that's a scheme of it. Simply the same thing. They've done the inferior planets. Both lots suggest doing the inferior planets really the same way that I did, because it's the least complicated for the inferior planets. Now, the difference is this, that I chose to complicate my model to show what was possible and to show that by using compound gear trains, which I can fit into my sort of reconstruction, you can get very, very good period relations for the planets indeed. They're all as good as that period relation for the moon that I mentioned earlier. In other words, all my planets, their mean position doesn't go wrong by as much as a degree in over 500 years. And frankly, though I say it myself, that's impressive. The other method of doing it obliges you not to use compound gear trains, but to use simple gear pairs, and you have to accept much less good approximations for the motion. And particularly, the motion for Venus is absolutely rotten. But the latest news is this. The ongoing reading of inscriptions, this is a thing which Alexander Jones very kindly told me ahead of publication. He's read the name of the planet Venus, it is Aphrodite, and the number 462. So what? What it shows is we're dealing with, again, as before, with Babylonian ratios, which go back very long time, and therefore, because they've taken over a very long period, they can be very good. Don't worry, Mike, I'm nearly at an end. But the Babylonian ratio for Venus is the good one, is 1151 to 720, and 1151 is bad news because it's a prime number. So you've got to approximate this ratio, and approximating it, this is in the latest paper that I've published, approximating it by means available to the Hellenistic mathematician, the best approximation you can come with is 462, that number again, to 289, and 289 is 17 squared. So we have numbers that can factorize and can be mechanized in a compound gear train. Not in simple gear pairs, but in a compound train. The simple gear pairs have to rely on this very poor approximation, 8 to 5. And that's embarrassing, actually, because it means that only after a couple of years, your Venus is going to be in the wrong place. In fact, this approximation is good enough to satisfy my criterion. It's still at least as good as the approximation for the position of the moon. Good to over less than 1 degree in 500 years. And with all the Babylonian numbers, you can do the same thing. If you have one planet with a compound gear train, the probability is you have all of them with compound gear trains. It may be that further reading of the inscriptions will throw up other numbers which will either prove or disprove this point. So I'm telling you really the latest thing, as far as I'm concerned. And the wonderful thing is that these Babylonian ratios can be fitted into compound gear trains, which can be put straight into my model instead of the gear wheels I have, with no other redesign than to just change the gear wheels. So I think I've come as near to the truth with this as present information allows. And with that view of my slightly cleaner model now on display in Athens, I'll stop.
You have a short movie?
Oh, have I time? Mike's kindly allowed me 3 minutes to show a little video. If we could have it, please. Now, this was made by a friend of mine for an exhibition in Florence. So the captions, you're starting with what you know. This is that fragment A. So his captions are both Italian and English. He made this at the same time that I was making that second model, and I gave him the data as they came available. So it represents pretty closely what's inside my second model. It's like a sort of reversed explosion. Here is the gear train leading from the sun to the moon. There's the gearing for the back wheel. I haven't explained why the gearing for the sun and moon is a disaster, but maybe that'll come up later. So there's the gearing for the back dial all coming together now. I love the way the little cotters fly into place. Upper back dial, lower back dial. Top is to the left in this case. Now you see the conjectural reconstruction of the planetary motion coming in. Planetary motion plus that pulsed motion, the solar anomaly. Those are the inferior planets. Here comes the sandwich for Mars. Now Jupiter, exactly the same pattern, only with different numbers of teeth and different geometry for the epicycle. And the same again for Saturn. And there's the front dial. And a set of hands. I'm sorry, I'm standing in your way. I've only just realized. Stupid of me. My day of the month dial is a conjectural edition, which we might discuss if you want later. There's the lunar phase, which is by no means conjectural. It's for real. And my... Yes, if you watch carefully, you can see some of the... There's Venus going Saturn going retrograde. Here is Jupiter going retrograde. And that's what you would see on my model if you could only turn the knob at a steady rate. I think my friend who made this animation is cleverer than I, really. I can't do this sort of stuff. No, one turn of the knob is something like 72 to 73 days. It's very odd.
Okay, unbelievable.
Thank you.
Come up. Okay, stop that. Now we're scrambling to save time. What I'm going to propose is that we not do the questions. There's only half a dozen, and you can ask them of Michael during the break. Nick, if you would please come up. Nick Alexopoulos is an emeritus professor in computer science and electrical engineering from UC Irvine with a broad fascination with all things ancient, scientific, and technological. And he's got about, I think, 20 minutes of discussion to give you a broader context for where this and other machines came from. So Nick, all yours.
Thank you. This is, and then moving forward. Okay. Thank you. How did it all begin? Well, because of the 20 minutes, I will be very quick, but I will cover at least 20,000 years. Always, the simple folk, like the sponge divers, are in simple clothes, and the government officials, of course, take all the credit at the end of the day, at the top. And I wanted to just demonstrate, this is from the National Museum of Athens. It's a book, and it has this picture. And I want to challenge you to think about, what do you see? I see pure technology. Some of you will say, well, I see technology right there. Some of you will say, I see art. And part of the mix is that the word technology comes from the ancient or modern Greek word technologia, techni and logos, where the meaning actually is, I make useful things with logic analysis with aesthetic value. So, in a nutshell, this is amazing technology as well. Because imagine the science or engineering of metallurgy to do such a kind of a statue. And I'll get back to this later. But how did it all begin? And I will take a little digression. It all started this morning for all of us when we got up and get ready to come here. We went through a very simple routine. We do this every day. We ate breakfast, we got ready, we got dressed. Maybe because we have become a little bit robotic, we had to touch our cell phone, see who sent us a message. We sent messages, we looked at pictures, etc. We got in the car, maybe we used GPS, and we came here. What a beautiful routine. We go through this every day for different goals. In this routine, we touch a huge number of objects, things. We touch them consciously, subconsciously. It's our life. We never think how those were made. Who amongst you is honest enough to tell me that one day you looked at your fork and you said, who is the engineer back then who figured out how to make this fork? And what about the engineer who made an assembly line to make millions of these so they're affordable and cheap? When you dial a number to call on your cell phone, do you ever think, how is this happening? What's in that little thing, the cell phone? We hear about chips. They have billions of transistors in an area smaller than your little nail. So you type the numbers, they convert into some electrical currents, signals, they go to the antenna, there the current piles up, bubbles out into a wave, electromagnetic wave, which spreads in space with the speed of light. It touches millions of cell phones, but it's only yours that receives that number. Magic. You never think about engineers. They're always in the background. You don't know that every working engineer creates 7 to 10 non-engineering, well-paying jobs. It is the economy, because all the things you see, you use, go through some simple or extremely sophisticated engineering. We say we are the most powerful country in the world. What do we mean by that? We mean we have the best weapons. Who makes those? It's all engineers. What am I trying to say? We never worry about our future. We're ahead of everyone. So did my ancestors. What you saw is only one device that we were fortunate enough to find. Otherwise, we would believe what I first heard when I came to this country, 1959, as a 17-year-old at the University of Michigan. Ancient Greeks had philosophy, had theater, blah, blah, art, architecture. No technology, no gears. How do you respond if you have no proof? So that's the proof. The other thing they never thought is they were so superior that they would exist forever. Yet, what you see in the Roman shipwreck is a standard process of the destruction of the ancient Greek civilization, which took several centuries, and it was obliterated. And therefore, we had to rediscover all this technology, the science, the mathematics, and so on. Can it happen to us? How do we store our knowledge? If what happened to them happens to us, it will take at least 10,000 years to recover what we know today. Think about that. So, I will very quick. Technology always defines our ages. We start with Stone Age, we go Bronze Age. Today, it's the Information Age. Now, I will say very few things, and please don't misunderstand me. I don't want to insult anyone, but I will start a little bit with religion, ancient Greek religion, the way I understand it. They believed in one God, known and unknown. It always has a duality. Known because of everything they see. Unknown because of the vastness of the universe. And of course, they didn't have all the devices we have today to study the cosmos. They also believed this is one entity is powerful, the most powerful. But it cannot only be good. Because if it's so powerful and only good, how does it allow evil to happen? Earthquakes in Nepal, for example. Or people killing one another. So therefore, that entity is both good and evil. Then they humanize that entity for all the human faults and goods we see. And they have layers of gods in their pantheon. And the Olympian gods each represents an entity of this one, known and unknown. So those Olympian gods 6 men, 6 women. And there you see a lesbian woman and a homosexual man, and also a god of technology. Hephaestus in Greek, Vulcan in Latin. Technology was praised in the society, even though there was no writing. It was through poetry, and we have Homer's poetry until it was written down. And in the Iliad, as well as the Odyssey, you have more than 800 praises, exaltations of technology. What were the industries? Let's say from the mythological times, we jump to the Hellenic period or the classical period, the glory of Athens and so on. We don't have time to go through details, so I'll be very quick, but had amazing shipping technologies. Assembly lines to make ships, warships, commercial ships. Shipping was the way of communication around the world for them. Weapon manufacture, mining, the mines of Lavrio near Athens, where they got silver and they became a wealthy state to support all these technologies, etc. I will just spend a little bit on this beautiful temple. You know, modern scientists, engineers, mathematicians have spent over 30 years now trying to understand how this was built. And I'm not going to spend time on any details other than I will take one column. And you see the column, the diameter of the column, as you go in height, diminishes. Each of the drums or sections fits perfectly. You hardly see the line between the different parts. But that's not it only. Inside, there is a hole, vertical hole inside each drum that matches through down to the ground. Why was that hole there? When the Parthenon was reconstructed the first time, a German engineer put an iron bar through. They assumed that's what they did for stability. Well, after a few years, the marble started eroding. The ancients were using lead, so it preserves the marble, but also gives elasticity during earthquakes. So they were better engineers. Now, is this technology or is it art? This is in the Museum of Delphi. What is it? Look at that. This was buried on the ground. Look at the eyes, look at the eyelashes. This is bronze. What kind of engineering or metallurgy is this? Isn't this amazing? Look at the eyes, different colors. Actually, when you look at it and you turn around, it follows you. So what did the ancient Greeks strive for? Perfection. Everything they did. The competitiveness amongst themselves was perfection. And if you read through their scholarly works, you can find a way of explaining that, and I derived a simple equation. Excellence plus harmony. Excellence is easier than harmony, because harmony means not only within yourself, but also with other people. So that's why perfection is not reachable in reality. However, if you look at this statue, and so many others, like the Antikythera youth we saw in the beginning, it's amazing technology, it's amazing art. Now, we lost so much because of all the distractions. We were systematic. I'll go through them very quickly, and I can answer questions later. We didn't know anything about this man. Where is Cyrene? Well, he was mentioned in one of Plato's dialogues. The title is the Theaetetus. Theaetetus was an ancient Athenian mathematician who was fantastic, but there is nothing left of his work other than what we found from others. Theodorus was a mathematician in Cyrene, Kyrene, in the called Pentapolis, the 5 Greek cities. Did you know that today's Benghazi was a Greek city called Phereniki? You don't. That's what I mean by everything had been destroyed and buried. There, you see ancient Greek ruins. It was one of the first religious uprisings against pagans, Greeks, that destroyed this, and Romans rebuilt the temple. Now, Theodorus did amazing work, apparently, the little that we have being able to understand, on studying irrational numbers. And he studied them in a way that I can explain later through geometry, but look at that. This is a book in 1993 by an American professor of mathematics. Imagine, 2,500 years later, people are studying the mathematics of Theodorus. So what have we lost? These are the continuous equations of Theodorus. I have given this here, the spiral of Theodorus and the spiral of Archimedes, because I'll come back to the spiral of Archimedes later. Now, we go to the Hellenistic period very quickly. It starts when Alexander the Great died. To 415 AD, it's a very critical year, because the first woman scientist mathematician was murdered by Christian monks, chopped up and burned, because she was still a pagan. Ptolemy was one of Alexander's generals. He took over Egypt and brought his body there and buried it, and still don't know exactly where. But he was amazing in terms of creating an amazing empire eventually, the Alexandrian Empire, but also because he created the Library and Museum of Alexandria, which I refer to as the first research university in the history of mankind. And I spelled here the word museum in the Greek way, but then how did he do it? He invited Demetrius of Phaleron, a known man, who was the governor of Athens for 10 years. He was a student in the Aristotelian way of thinking, and he is the one who was the intellectual founder of the museum and the Royal Library. And this is presumably what he looks like. Phaleron is a suburb of Athens by the sea. Now, I will go through this because we don't have time. These are full lectures by themselves. In the Library of Alexandria, we have the development of amazing science, mathematics, astronomy, technology, and medicine. I will not touch medicine, but the first anatomy was done in Alexandria. The first examination of the brain was in Alexandria. The first understanding of the women body was done in Alexandria, because the first time that human beings started anatomy, meaning to touch and open up human beings to understand how we function. The Ctesibios were studying pneumatics, and that is the combination of fluid mechanics and air pressure. He created an amazing musical organ, and who would believe it? He was the son of a barber, and here's the organ, a reconstruction, where you needed somebody to pump air, and the musician was playing the valves. The musical organ has pumps, pistons, intake valves, inverted cisterns, and pressure chambers, etc. It had what we have in cars today. Later on, I can read to you an analysis of this by a very famous professor of mechanical engineering and fluid mechanics, if we have time later, not in this part of the talk. Here is a proof that this was actually done. And this is in a museum in northern Greece, a musical organ from 150 BC. And I hope somebody like Michael takes this up to really do a thorough analysis of the mechanical parts and the brilliance of this machine. Now, I had given lectures on this topic more than 10 years ago. There were audiences of this size. People were encouraging me to write a book, but somebody saved me. I was beginning to write a book. This is a book written by an Italian professor of mathematics and philology, The Forgotten Revolution, How Science Was Born in 300 BC and Why It Had to Be Reborn. It's an amazing book where he systematically shows the science and technology that disappeared because of religious fanaticism. Here's another book, the Archimedes Codex. I will spend a few minutes with this. The authors are Reviel Nedge is a professor at Stanford of archaeology and mathematics, the ancient mathematics. So, what is this? This was a prayer book, a Christian prayer book. Somebody saw in Constantinople, today's Istanbul, 1000 AD. But he noticed that under the Christian prayers, there was something else written in ancient Greek. That book disappeared from Istanbul, today's name. Then it was seen in a monastery in Lebanon. Then it disappeared from Lebanon. Then it was found in the possession of a French family who actually sold it in an auction in New York about 16 or so years ago, anonymously, to an American. He bought it, he gave it to a museum in Baltimore. And the funds to analyze it with three-dimensional imaging to see what is written under the Christian prayers. And under the Christian prayers is one of Archimedes' original works. Under a prayer to the dead, there is the definition of science, exactly the definition we use today. And then proving that he was the inventor of integral calculus, that he established probability, because he was studying how many particles of sand are there in the universe. And he was a phenomenal engineer, incredible engineer. And his mathematics was incredibly sophisticated for the time. So we have now modern proofs of these things, because when the ancient Greek world was destroyed, how would people write? What they did is they took ancient Greek texts, which were using vellum, animal skin, which was invented in Pergamum, today's Bodrum in Turkey, and they erased the ancient texts and wrote Christian prayers. If the writing was this way, they erased it and they wrote the vertical way. Fortunately, we found this, just like the mechanism. Hopefully, we'll find a lot more evidence of the sophistication of that society. And remember, they never thought that they would be destroyed. Think about that. Now, first, the destruction was when Caesar was trying to conquer Alexandria to support Cleopatra, whose brother was actually fighting her. They say that part of the library museum, or at least the books near the harbor, were burned. But Emperor Theodosius ordered everything pagan destroyed. Libraries were burned, temples were destroyed. That's why you see statues without arms or noses. It was a superiority over the pagans, the ancient Greeks. This is by modern Greeks who became Christian, or other Christians. Then Emperor Justinian closed Plato's Academy. Imagine, it was functioning for 8 centuries. Also, Theodosius stopped the Olympic Games. Then the Arab conquest finished everything off. And there is this discussion. The general who took over Alexandria sent a message to his boss, what shall he do with whatever books he found in the libraries? And that was the argument. And I was burn them, they're useless. Now, there is also an argument between these two authors. One is an Egyptian, and he argues, oh, this didn't happen. Yes, Arab sources are telling us, Muslim sources are telling us that this happened by Arabs. But these sources are a few centuries later than the event. Whereas the Italian, Luciano Canfora, is arguing that it was not Caesar that destroyed the library first, because another historian, Strabo, was there 2 centuries later and was describing the library. Now, this is the first woman scientist, mathematician, who, in the fanaticism of the Christian world, in some ways, when I look back, it is Rome's fault because there's amazing persecution against the early Christians. You remember that? So when Christians became large in numbers, they dished it back. And it was really vicious. Anyway, she was still teaching the ancient Greek way, not through Christianity. And she had students who were Christians, Jews, as well as pagans. Imagine it took all these centuries to have another woman scientist. In between, intelligent women were burnt on the stake. Imagine that a movie was made in Spain a few years ago about her. And imagine that the church in Spain managed to make sure it is not shown in Spain. Now, what was she saying to be killed? To know one religion is not to know that one. Wow. Superstition consists of one thing: faith to one religion to the exclusion of others. To know one philosophy is to know none. To rule by fettering the mind through fear of punishment in another world is just as base as the use of force. Because ancient Greeks did not believe in hell. They believed in the underworld where everybody goes, sinners and good people and so on. So anyway, the Bishop of Alexandria, who essentially ordered her death, became a saint. I'm showing this to challenge a little bit Michael and many others. And I will discuss this a little bit more. This kind of shape is actually from 20,000 years BC. And you see it periodically in various cultures, this double spiral. And it has to do with the calendar, how primitive people were counting months and a season and a full year. Well, a young engineer by the name Senghua Yun derived the equations exactly for the calendar that Michael showed us. These are Archimedean spirals, and these are the equations to reproduce those spirals. It may have nothing to do with the actual calendar of the mechanism, but I thought I'll throw it there for fun. I'm done. Thank you.
Thank you. Wonderful. In the interest of time, by the way, you've been an incredible audience. I can tell when information is going right in and being received, and this has been a very special morning. I'm sure the afternoon will be as well. Michael will be demonstrating the device in the foyer out here. We've got about, is it an hour for lunch, John? Roughly 1 hour for lunch. Stretch your legs, see how the machine works, grab a bite in the cafeteria, and come back here for the afternoon to find out what we're going to learn next about Antikythera.